Hey everyone, welcome back to WECM with Max. I'm absolutely thrilled to have you join me today as we dive deep into one of the most fascinating and foundational topics in blockchain technology, cryptographic hashing. Whether you're just starting out in the world of cryptocurrencies or you're a seasoned pro looking to solidify your understanding, this video is designed to unpack everything you need to know about hash functions, their critical role in blockchains, and why they're so essential to the security and functionality of systems like Bitcoin. So grab a notebook, maybe a cup of coffee, settle in, and let's embark on this exciting journey together. Before we dive into the technical details, let's take a moment to appreciate why hashing matters. Hashing isn't just a buzzword in the blockchain space, it's a fundamental concept that permeates all of computer science. Think about it. From securing your passwords when you log into your favorite website, to organizing massive datasets in hash maps, hash functions are the unsung heroes working behind the scenes. In cryptocurrencies, they take on an even more pivotal role, acting as the glue that holds the entire system together. They ensure that data remains untampered, transactions stay secure, and miners can prove their computational work. By the end of this video, you'll not only understand what makes a hash function cryptographic, but also why it's so incredibly difficult to break and how it's applied in real-world blockchain scenarios. Plus, we'll have some fun exploring a deliberately flawed hash function to see exactly what not to do. Are you ready? Let's jump right in. So, what exactly is a hash function? At its heart, a hash function is a mathematical process that takes any kind of input, whether it's a short string like your name, a massive file like a movie, or even a single number, and transforms it into a fixed length output called a digest or hash value. Imagine a blender in your kitchen. You can toss in a handful of strawberries, a banana, or an entire pineapple, but no matter what you put in, the blender churns out a consistent smoothie. That's what a hash function does. It takes inputs of any size and produces an output of a predictable length. This fixed length property is crucial, and we'll explore why it's so important in just a moment. To bring this concept to life, let's look at a deliberately oversimplified example, a hash function I'm calling bad hash. Now let me be clear, this is not something you'd ever want to use in a real system. It's purely for learning purposes to help us understand the mechanics of hashing. Picture bad hash as a toy version of a hash function. It takes a string, like your name, and converts each character into its ASCII value. If you're not familiar with ASCII, it's a standard system that assigns a number to every character. For example, the letter A is 65, B is 66, and so forth. Bad hash adds up all those ASCII values and then takes the sum modulo 256, which ensures the result is always a number between 0 and 255, or in hexadecimal 0x00 to 0xFF. This gives us a 1-byte output, no matter how long the input is. Let's try it with the name Max. In ASCII, the letter M is 77, A is 65, and X is 88. Add them up, 77 plus 65 plus 88 equals 230. Now take 230 modulo 256, which is still 230, or in hexadecimal, 0xe6. So the hash of Max, using bad hash, is 0xe6. Let's do another example to drive this home. Take the name Bob. In ASCII, B is 66, O is 111, and B is 98. Add them up, 66 plus 111 plus 98 equals 275. Now 275 and modulo 256 is 19, or in hex 0x13. Here's the key takeaway. Whether the input is a 3-letter name like Max or a 10,000-word novel, bad hash always produces a single byte, a number between 0 and 255. This fixed length output is a hallmark of all hash functions, and it's what makes them so versatile. Why does this matter? Hash functions are incredibly useful across computer science. For example, in a hash map, a common data structure, they determine where to store data in memory based on the hash of a key. If you've ever used a dictionary in Python or a hash map in Java, you've benefited from hashing. In distributed systems, like a cluster of servers, hash functions help decide which server should store a particular piece of data, ensuring an even spread across the system. In blockchains, hash functions are the backbone of security and integrity. They ensure that transactions can't be altered, blocks are linked securely, and the entire system remains trustworthy. But here's the catch. Not all hash functions are suitable for blockchains. For that, we need cryptographic hash functions, which have specific properties that make them secure. Bad hash, as you might guess, is going to fail miserably, and we'll explore why in just a bit. So, what makes a hash function cryptographic? In the world of blockchains and cryptocurrencies, we need hash functions that are not just functional but also incredibly secure. A cryptographic hash function must have 3 essential properties. It should be collision resistant, hiding, and puzzle friendly. These properties are what make hash functions like SHA-256 the gold standard for blockchains. Let's break each of these properties down, explore what they mean, and see why our toy example, bad hash, falls short in every way. First, let's talk about collision resistance. A hash function is collision resistant if it's practically impossible to find 2 different inputs, let's call them x and y, that produce the same hash output. In technical terms, if hx equals hy, it should be extremely unlikely for x and y to be different. Why is this so important? Imagine you're running a blockchain and you hash a transaction message like send 10 BTC to Alice, which produces a hash of 0x77. If an attacker could find a different message, like send 100 BTC to Bob, that also hashes to 0x77, they could swap the messages, and no one would notice. That's called a collision, and in a secure system, it's a catastrophic failure because it undermines trust. Bad hash is a disaster when it comes to collision resistance. Since it only produces 256 possible outputs, 0 to 255, finding collisions is trivially easy. Think about it. There are infinitely many possible input strings. Your name, a sentence, an entire book, but only 256 possible hash values. By the pigeonhole principle, many different inputs must map to the same output. For example, if you hash attack at dawn and get 077, an attacker could craft a completely different message like sit down and meow that also sums to 0x77 by carefully choosing characters with the right ASCII values. With only 256 possible outputs, it's not hard to find such collisions, especially with a bit of trial and error. In contrast, a cryptographic hash function like SHA-256 produces a 256-bit output, which means there are two 256 possible hash values, a number so large it's practically unimaginable. Finding a collision for SHA-256 would require an astronomical amount of computational power, far beyond what's feasible even with the most advanced supercomputers today. Now let's address a subtle but important point. True collision-free hash functions don't exist. Why? Because we're mapping an infinite set of possible inputs to a finite set of outputs. Mathematically, collisions are inevitable. There are simply more inputs than outputs, so some inputs must share the same hash. The key is designing a hash function where finding those collisions is so computationally difficult that it's effectively impossible. That's what collision resistance means. Not that collisions don't exist, but that they're so hard to find that no one can exploit them in practice. Bad hash fails this test spectacularly, while cryptographic hash functions like SHA-256 are designed to make collision attacks infeasible. Next up is the hiding property. A cryptographic hash function should be a one-way function, meaning that if I give you the hash value hx, you shouldn't be able to figure out what x is. This is critical for protecting sensitive data. For example, when you log into a website, your password is often hashed and stored as a hash value. If someone steals the hash, they shouldn't be able to reverse engineer your password. This one-way nature is what makes hashing so powerful for security. Bad hash is terrible at hiding. Because it simply sums the ASCII values of the input characters, it's easy to manipulate the input to produce a specific hash. If I tell you the hash of a message is 0xE6, you could try different combinations of characters that sum to 230 before modulo 256 and work backward to guess the input. For instance, knowing that max M77 A+65 X88 hashes to 0xE6, you could try other strings with the same ASCII sum like AAB, A65, A65, B66, totaling 196 plus 34 to reach 230. This makes bad hash completely insecure for hiding data. In contrast, a cryptographic hash function like SHA-256 scrambles the input so thoroughly that reversing the hash is computationally infeasible. This property, known as pre-image resistance, ensures that even if an attacker has the hash, they can't figure out the original input. To get a bit more technical, hiding also means that if you prepend a secret value, called a nonce, to the input and hash it, no one can guess the input even if they know the hash. A nonce is just a random, one-time use value that adds an extra layer of security. This is crucial for applications like commitment schemes, which we'll dive into later. For now, just know that bad hash fails at hiding because its output is predictable and manipulable, while a good cryptographic hash makes it virtually impossible to reverse engineer the input. The third property of a cryptographic hash function is puzzle friendliness, which is especially important for proof-of-work blockchains like Bitcoin. Puzzle friendliness means there's no shortcut to finding an input that produces a specific hash output. If you're trying to find a hash that starts with, say, 10 zeros, the only way to do it is to try millions or billions of different inputs until you get lucky. There's no clever trick or formula to predict the output without doing the computational work. Bad hash is not puzzle friendly at all. Since it's just a sum of ASCII values modulo 256, you can systematically tweak the input to get a desired output. For example, suppose you want a hash of 000. You could start with a string like ishbib A and calculate its hash. A is 97, so 3 A's give 97 plus 97 plus 97 of 291, and 291 modulo 256 is 35 or 0x23. To get to 0x00, you could adjust the characters, maybe switching to a character with a lower ASCII value like the equal sign, or else ASCII 61. Try A 97 plus 97 plus 61 power 255, and 255 modulo 256 is 255 or 0xFF. Now try A, where is 62, 97 plus 97 plus 62, about 256, and 256 modulo 256 is 0, or 0 also 0. Boom, you've hit your target with minimal effort. This predictability makes bad hash useless for cryptographic purposes, as it allows attackers to bypass the need for brute force computation. In contrast, a cryptographic hash function like SHA-256 is puzzle-friendly, because even a tiny change in the input, like adding a single character, produces a completely unpredictable change in the output. If you want a hash that starts with 10 zeros, you have to keep trying different inputs, typically by changing a nonce, until you find one that works. This brute force process is what makes proof of work in Bitcoin so computationally intensive and secure. There's no shortcut, you just have to do the work. To really drive home why bad hash is such a bad idea, let's explore a few scenarios where it would fail miserably in a blockchain context. Suppose you're using bad hash to secure a blockchain. You hash a transaction like send 10 BTC to Alice, which gives you a hash of URCA77. An attacker could easily craft a different transaction, like send 100 BTC to Bob, that also hashes to URC77 by manipulating the ASCII sum of the characters. Since bad hash only has 256 possible outputs, finding such a collision is straightforward. You could even do it by hand with a bit of patience. In a real blockchain, this would allow attackers to forge transactions, completely undermining the system's security and trustworthiness. Now let's consider hiding in a practical context. Imagine you're using bad hash to store a secret message, like a password or a private key. If an attacker gets hold of the hash, say 0xC6, they could try different combinations of characters that sum to 230. Since the output space is so small, they could quickly guess inputs like max or other strings with the same ASCII sum. This lack of hiding makes bad hash useless for protecting sensitive data. In contrast, SHA-256 produces a 256-bit output that's so scrambled and unpredictable that reversing it is like trying to unbake a cake. You'd need to try an infeasible number of combinations to crack it. Puzzle friendliness is where bad hash fails most spectacularly in a blockchain context. In Bitcoin, miners compete to find a hash that meets a specific target, like a hash that's below a certain numerical value, often represented as starting with several zeros. This process, called proof of work, requires miners to try billions of different nonces until they find one that works. With bad hash, you could simply adjust the input characters to hit the target hash, bypassing the need for computational effort. For example, if the target is a hash of ERIC00, you could tweak the input string as we did earlier, adding or subtracting characters until the ASCII sum modulo 256 hits 0. This predictability destroys the security of proof of work, as it allows anyone to cheat the system without doing the required work. In contrast, SHA-256's puzzle-friendly nature ensures that miners must perform real computational work, making Bitcoin's network secure and resistant to attacks. Now that we've thoroughly trashed bad hash, let's shift gears and talk about the real heroes of cryptographic hashing, the hash functions actually used in blockchains. In Bitcoin, two of the most prominent hash functions are SHA-256 and RIPMD160. These are battle-tested, widely respected, and designed specifically for cryptographic security, making them ideal for the demands of blockchain technology. SHA-256, developed by the National Security Agency, produces a 256-bit or 32-byte hash value. It's used extensively in Bitcoin for tasks like hashing transactions, creating block headers, and powering the proof-of-work system. RIPMD160, a 160-bit hash function, is often used in Bitcoin for generating wallet addresses, as it produces a shorter hash that's still secure but more compact. Both of these hash functions are collision-resistant, hiding, and puzzle-friendly, which makes them perfect for the high-stakes world of cryptocurrencies. Let's see SHA-256 in action to understand why it's so effective. If I hash the string I with SHA-256, I get a long, seemingly random string like 63C. I'm abbreviating for simplicity, but it's actually 64 hexadecimal characters. Now, if I change just one character, say from A to AB, the output changes dramatically to something like F7B. This is called the avalanche effect. A tiny change in the input causes a massive, unpredictable change in the output. With bad hash, changing A to AB would just increment the output by 1, since B's ASCII value is 1 higher than A's. But with SHA-256, the entire hash flips in a way that's impossible to predict without running the hash function again. This sensitivity to input changes is what makes SHA-256 so secure for cryptographic purposes. To quantify this, a good cryptographic hash function like SHA-256 ideally changes about 50% of the output bits for every single bit changed in the input. This randomness and unpredictability are what make it so hard to reverse engineer or manipulate. For example, if you're trying to find a collision, two different inputs that produce the same SHA-256 hash, you'd need to try on the order of 128 attempts, half of 256 due to the birthday paradox, but that's a topic for another video. That's a number so large, it's effectively impossible with current technology. This is why SHA-256 is trusted for securing Bitcoin's blockchain. It's important to note that no hash function is proven to be perfectly secure. Cryptographic research is an ongoing field, and even widely used hash functions can develop vulnerabilities over time. For example, SHA-1, an older hash function, was once considered secure, but has since been found to have weaknesses that make it unsuitable for cryptographic purposes. It's still used in non-cryptographic contexts like versioning in Git, e.g., for GitHub commits, but for security-critical applications like blockchains, it's been replaced by stronger functions like SHA-256. While SHA-256 is currently considered secure, the blockchain community remains vigilant, always testing for potential weaknesses and ready to adopt new hash functions if necessary. This constant scrutiny is part of what keeps cryptocurrencies robust and trustworthy. Now let's explore how cryptographic hash functions are actually used in blockchains. They play a starring role in three key areas: ensuring data integrity, enabling commitment schemes, and powering proof of work. Let's dive into each of these applications to see how hashing ties everything together. First, data integrity. In a blockchain, every block contains a hash of its contents, including all the transactions it holds, and a reference to the hash of the previous block. This creates a chain of hashes, linking each block to the one before it. If someone tries to tamper with a block, say by changing a transaction from send 10 BTC to Alice to send 100 BTC to Bob, the hash of that block will change. Since the next block references the original hash, the tampering will break the chain, making it obvious to everyone on the network. Because SHA-256 is collision resistant, it's virtually impossible to find a different block that produces the same hash, so the tampering attempt fails. This is how blockchains like Bitcoin maintain trust without relying on a central authority. Everyone can verify the integrity of the chain by checking the hashes. Let's break this down with an analogy. Imagine a blockchain as a stack of locked diaries. Each diary block has a lock that can only be opened with a specific key, the hash of its contents. The key for the next diary is stored inside the previous one, linking them together. If someone tries to rewrite a page in one diary, the key changes and it no longer unlocks the next diary. Everyone notices the mismatch, and the tampering is exposed. SHA-256's collision resistance ensures that forging a new key to match the original is so hard it's effectively impossible, keeping the blockchain secure. Next, let's talk about commitment schemes, which are a clever use of cryptographic hashing. A commitment scheme lets you commit to a value without revealing it, then prove later that you knew it all along. Here's how it works. Suppose you want to predict the price of Bitcoin a year from now. Say, Bitcoin will hit $100,000. You don't want to reveal your prediction yet, maybe because it might influence others or you're making a bet with friends. So you take your prediction and append a random nonce, a one-time use value like 37390129230011. You hash the combined string, Bitcoin will hit 100,000 plus the nonce using SHA-256, and you get a hash like EB97. You publish this hash publicly, maybe on Twitter or on the blockchain itself, as your commitment. Later, when Bitcoin hits $100,000, you reveal your original message and the nonce. Anyone can take those two pieces, concatenate them, hash them with SHA-256, and verify that the result matches the hash you published earlier. If it matches, it proves you made the prediction, without anyone being able to guess it beforehand. The hiding property ensures that no one could reverse engineer your prediction from the hash, and the collision resistance ensures that no one could find a different message and nonce that produce the same hash. This makes commitment schemes incredibly powerful for applications like sealed bids, time-stamped predictions, or even secure voting systems in blockchain contexts. To make this more concrete, let's walk through an example. Suppose you're betting with friends on who will be the next US president, and you predict it'll be Max LeBoon. You don't want to reveal your guess yet to avoid influencing your friends' bets. So you take the string Max LeBoon and append a nonce, say 30739012923011. You hash this with SHA-256, getting a hash like AB97. You share this hash publicly, committing to your prediction. When Max LeBoon wins, grant we all wish, you reveal the string Max LeBoon and the nonce. Your friends can verify the hash, proving you made the right call. The nonce adds an extra layer of security, making it harder for someone to guess your prediction by trying common names, as the nonce's randomness ensures the hash is unique. Finally, let's talk about proof of work, the engine behind Bitcoin's security. In Bitcoin, miners compete to add new blocks to the blockchain by solving a computational puzzle. They take the block's data, including transactions and a nonce, and hash it with SHA-256. The goal is to find a nonce that produces a hash below a specific target value, often one that starts with several zeros. Because SHA-256 is puzzle-friendly, there's no shortcut. You have to try countless nonces until you find one that works. This process is computationally expensive, requiring significant energy and hardware, which is why Bitcoin mining uses so much power. The puzzle-friendly nature of SHA-256 ensures that miners can't cheat the system. The only way to find a valid hash is through brute force computation, trying billions of nonces. This makes the network secure because an attacker would need to outcompute the entire network to rewrite the blockchain, a feat that's practically impossible with Bitcoin's massive mining power. For example, to create a block with a hash starting with 10 zeros, a miner might need to try trillions of nonces, each requiring SHA-256 computation. This computational work is what secures the network and ensures that adding new blocks is a costly, verifiable process. To illustrate, imagine you're trying to unlock a safe with a combination lock that requires a 256-bit key. With bad hash, you could guess the key by systematically trying simple combinations, like adjusting a few numbers. With SHA-256, it's like the combination is completely random, and you have to try every possible combination until you get lucky. This brute force requirement is what makes proof of work so effective at preventing attacks and ensuring consensus in a decentralized system. Let's revisit bad hash one more time to see how it would fail in proof of work. If Bitcoin used bad hash, miners could easily manipulate the input to hit the target hash. For example, to get a hash of 0x00, they could adjust the nonce's ASCII values to make the sum modulo 256 equals 0, as we saw earlier with AA. This would make mining trivial, allowing anyone to create blocks without significant effort, destroying the security of the blockchain. SHA-256's unpredictability ensures that mining remains a challenging, resource-intensive task, which is why it's the cornerstone of Bitcoin's proof-of-work system. We've covered an immense amount of ground today, exploring the ins and outs of hash functions and their critical role in blockchain technology. We started with the basics. A hash function takes any input and produces a fixed-length output like a digital fingerprint. For blockchains, cryptographic hash functions like SHA-256 must be collision-resistant, hiding, and puzzle-friendly to ensure security. Our toy example, bad hash, showed us what happens when a hash function lacks these properties. It's easy to break, manipulate, and exploit. In contrast, SHA-256's robust design makes it ideal for securing transactions, linking blocks, and powering proof of work. In blockchains, cryptographic hashing is everywhere. It ensures data integrity by linking blocks in a tamper-proof chain, enables commitment schemes for secure predictions and bids, and drives proof of work to secure networks like Bitcoin. Whether it's verifying that a transaction hasn't been altered, proving you made a prediction without revealing it, or mining a new block, hashing is at the core of it all. In our next video, we're going to take these concepts and put them into action by building a simple blockchain from scratch. We'll create data structures, link blocks with hashes, and see how the whole system comes together in practice. It's going to be a hands-on, exciting continuation of our journey, so you won't want to miss it. If you found this deep dive into cryptographic hashing valuable, please give this video a thumbs up, subscribe to the channel, and hit the bell icon to stay notified about new videos. Got questions about hashing, blockchains, or anything else we covered? Drop them in the comments below. I read every single one and love hearing from you. Thanks so much for watching, and I'll see you in the next video.